First things first, better, the correct version of the string figure. It really was subpar. I don't know what I did wrong in it, but it was missing a few of the little, like, bits. Oh, mother! Got way too excited. Apparently my motor skills are at an all-time low. One more time, and then we'll go, oh, Labina! I'm so glad you're here.
Made it.
Yay, thank you.
You're wearing pink.
Yeah, we were all, yeah.
Were you all? My sister bought it from me.
Oh, that makes sense.
But you're all good. Okay, here it comes. That's the right version. Much better. It was like missing, it was half that subpar. Thank you. And then there's a game you can play from this. I don't know, somebody grabs the two things. Vivian, you kind of know what I'm talking about. Yeah, do you know how to do it?
I used to do it and like.
We'll have to come by my office one day.
Sure.
We'll like work this out.
Yeah, it's been a
Okay.
while, but.
We'll do this in seminar next spring.
Okay.
Alrighty, friends. So I do have a question for you right up front. A little warm up. Just a thing we're going to look at today in a couple of different ways. So today I want to cover the full scope of basically the numerical methods we're going to be talking about for the rest of the semester, essentially. They are the Runge-Kutta class of methods. We've talked about Runge-Kutta 1, that is the Euler's method that we talked about. That's RK1. I want to talk about that a little bit more, the error on that, how the error propagates when we run it, and then talk about RK2 and RK4. So that's kind of the plan today. I've got some nice code that I was desperately just, there might be a bonus in coming up, because I had a problem with my code. The behavior of it in this one situation was very, very disturbing. So let's see here. So Daniel's not here. I think Daniel's the only one who hasn't had diffie-q. So for my bathroom break, I would like you to please solve this problem. I'll be right back. you can assume the independent variables, probably you're feeling like it's x. If you went with x, that's cool. I was thinking t in my head, but so that's dy dx or dy dt. I just wanted to kind of see how much we needed to talk about the process of it. It's looking like probably we ought to talk about it. Yeah, that is correct. Absolutely. Yeah. Now you gotta do the part you might not be certain of. Yeah, that's good, but you did separate. So this is just to make sure you're on the right road. This is a separable equation. So you would first write that derivative as a quotient of differentials, then you would separate, probably, I see folks pull in this negative 4.25 underneath. I would leave it on the right and just go this way. I think it's always best to just leave those nasty numbers in the bottom. Otherwise you got this log, and then you're probably going to want to substitute to get it into a du over u form. And it just makes life more complicated than it needs to be. That's good. Now we're going to use this example all day today. I'll make something else while you do that. Let's actually maybe touch base a bit. If you're looking at a differential equation, especially first order, in particular first order, and you're honestly not sure how to solve it, so maybe you got to this stage and you're like, I don't have my integral table, or ChatGPT, or Wolfram, or whatever it is that gets things done these days. You could always create a direction field to at least get a qualitative sense of the solution. So I came over here into the YT plane, and I noticed that if y equals 0, I'm on the t-axis, but if y equals 0, and I plug that in here, so replace that y with 0, I see that y prime equals 0 when y equals 0, no matter what t is. So independent of t, if y is 0, the slope is purely horizontal, and I wind up immediately getting an equilibrium solution. So if I start on this line, think about Euler's method. Remember how Euler's method works. You take your initial point, you grab the slope at that point. So right here, I grab the slope at 0. I move h units, where h is our step size, to the right, grab the new slope, move h units in that direction, and repeat. So via Euler's method, or just via intuitively understanding these d fields, I see that if this had been 0 here, I could have just said y is identically 0. But it isn't. We got y equals 1. So at 1, what's happening? At the point 0, 1, which is t equals 0, y equals 1, I've got a slope of, this is my formula for the slope, right? This is the slope at the point ty. Notice it's totally independent of t. So that means once you know the slope at a y value, on a horizontal line away across, that slope is constant. So this slope is independent of t. It depends purely on y. This is starting to look a little saggy here. So maybe bring these arrows up. But I was trying to estimate a slope of -4.25 all along there. So all along this line here, I've got, those are the directions I'm going to head when I'm on that line. And then from there, I can kind of like intuit what the solution might look like. So let's think Euler's method. Like seriously, Euler's method is how you navigate yourself simply on these direction fields. So you go here, your slope is -4.25. Move at that slope, super steep, downward to the right, for some step size, whatever that is. That's my h, that horizontal component there. So if this was half a unit, then I would actually be going down half this number, so -2.125 down. That's not too bad there. And then I grab that new point. Now, what do you think is happening to the slope between these two bands? Is it becoming more negative or less negative as I move from here down to here? Less negative, right? It has to hit zero slope at some point. These slope fields are continuous. So a small change in position is a small change in the arrow direction. So what I'd see is in here, there's probably some arrows that kind of look like this at some point. Kind of an average of that and that. And then as I get even closer, they get even flatter. So I can kind of intuit that my solution would look like this. Now realize that's going to be asymptotic. Those arrows are never going to have zero slope, and they're always going to be just getting you closer and closer to this, but never getting there. And I could backward engineer this and realize that as I move up, the slope gets steeper, and I probably got something that looks like that. So I can feel what the solutions look like. If I started down here, I would see in a similar way that the solutions, so there's this families of curves that no matter where I start, this is going to be my behavior. And so this is a qualitative analysis. I understand the whole thing at once. There we go. Hey, that equilibrium, is that a stable equilibrium or an unstable equilibrium? Stable, why do you say that, Cormac?
Because from both sides, they're going to the same equilibrium.
Yeah, exactly. So talking in the language of perturbation, if I was on this equilibrium solution, but I somehow got knocked off of it because of noise or error in the computer program or whatever, I would immediately be brought back to it. Now, I would never come fully back to it, but I would be at least headed back toward it. So remember, stable equilibrium, that, unstable equilibrium, it's that. That's super unstable. Cool, so we kind of already know this, but then we can get an explicit solution by using separation of variables, which is the only technique I will ask you to know on the final at all. Separation of variables says take your derivative, write it as a quotient of differentials, separate the variables based upon the variable in the differential. There's no t's in here, so I'm just going to leave that guy over there. Put the y under here. Integrate as your last step. You integrate with respect to each variable. So this goes to natural log of y, and this goes to -4.25t plus some constant. Then I want to undo this, because I really want to know y equals what. This is a totally valid solution. Totally cool, but it's implicit. We want explicit. Can somebody help me with that? How do I convert that to y equals something? Yeah, to use the exponential, right? That's what you're saying, I believe. Yeah, thank you, man. So this identity really is incredibly useful. But if you have this, it is 100% equivalent to this. These say the exact same thing. And I like to do it with boxes and triangles because sometimes there's a lot of stuff here or here. So doing that, notice that what's in the box is absolute value of y, what's in the triangle is negative 4.25t plus c. So absolute value of y equals e to that quantity. So e to the negative 4.25t plus a constant. Is there anything cool I could do at that point? I mean, that's cool. What would you do, Vivian?
It could be bring down the c to like times e to the c, and then c, that would be a new constant.
Beautiful. I love it. Perfect. So what Vivian's describing is using this lovely little trick that you're just acknowledging that this is this because you add exponents. And now this, notice this is always positive because it's e to some power. But it's just some constant. So I'm gonna call it c again. And I get that nice form that looks like this. Right now c is a positive number because I had absolute value over there. If I want, I can now strip off the absolute values and allow c to be positive or negative. So check this out. The absolute value of y is that where c is positive, but y itself could have a negative value here and would need to if we actually started in this bottom half of the plane, we would have to have c be a negative number. So we got our solution. Last thing to do is solve for the initial condition. Solving for the initial condition, I'm going to let t equal 0 and y equal 1. And from that, you're going to get e to the 0, which is 1. This implies that c equals 1. And our solution is just lovely. Yay. There's our true solution. And we're going to use that when we look at the code, the Runge-Kutta code. Is there any questions on this? I wanted to refresh our memory on that. Okay, cool. Is it okay if I erase? Anybody still need this up? Okay, I see a few folks ready. I'm going to erase slowly. Let's start over here. I want to talk real quickly about the error in Euler's method. So let's assume that we've got this differential equation, which says, excuse me, y prime equals some function of t and y, and I've got some initial condition that I want to satisfy. So when I find y that solves that, that's the true solution. We know that Euler's method doesn't produce the true solution. We just want to see how far off it is from the truth. So in Euler's method, with step size h, the y naught is that initial condition, but y1 is going to equal y naught. So if I'm right here, here's t naught, here's y naught, I'm right here. I'm going to find the slope here. How do I find the slope here? It's given by that formula. So f of t naught y naught is our current slope. And I'm kind of doing this just so we think about these things over and over again so that they really become more natural and they feel a little more familiar. So I'm going to add that, but that's the slope. I still have the step size that I want, and that is a distance of h. So if I move over h, I have to move up the slope, f of t naught, y naught, times h. And that's this height change here. And so I just multiply by h. That's Euler's method. And then y1, t1, so t1 is t naught plus h. That's your new point, right here. And here's your new y1. Repeat. Repeat until until you got what you want. Just keep doing that over and over again. So that's very elegant, very simple. But now let's look at the Taylor expansion. So this is very, very cool, and you'll get this. This is not a super deep observation, but it's an observation you wouldn't make unless you thought about the Taylor series. So if y tilde of t equals the true solution, and we just found that for a specific problem, but I'm saying for the general problem. Suppose I could solve that. I'm master of diffie-q, I whip out that formula, got it. Or some robot finds it, you know, whatever. Then that y1, the true y1, which is the next y value, the true y1 is equal to y tilde at t naught plus h. Again, remember y at t naught, y tilde at t naught is our initial condition. So if I move over h units, that is the actual true value. So I've got this weird, beautiful curve, that's the truth. Y tilde of t, here's t naught, here's t naught plus h. And that right there is y1. And let's call it, I guess, y1 tilde. I was experimenting with subtruths and all this stuff, but then there's like t's, there's too many damn t's. And this is the notation the book uses too, so you can check it out there. So let's do a Taylor expansion on this centered at t naught. So how do you do a Taylor expansion? It's the function at the center point plus the first derivative at the center point times h. Hello, Euler's method, much? Right, like right there. Plus y double prime at t naught over 2 factorial h squared plus a bunch of h cubed and higher things coming down the chain. Right, y triple prime over 3 factorial h cubed and so forth. Is this all good? Any questions or confusions? All right,
I have a
nice.
question.
Yes.
Why are we taking the Taylor series of that?
Because it's going to show us, what our error actually is.
But like, how does the Taylor series show error? Or maybe that will come up.
It will come up. It's
Okay.
not obvious yet.
Okay. 'Cause I'm like,
So it's kind of like we're in the car and I'm like, we're going to get to Disney World. And you're like, why aren't we at Disney World?
Okay. I'll
Just
trust
give me a
the
minute.
process.
Give me a minute. So this expression right here, let's see, wait, let me check out my notes now. Suddenly I was like, I've done this multiple times in my office and now suddenly I'll look at my notes and they seem completely alien. Oh, so put a tilde here. That's part of the problem because this is that true function right there. Nice, nice, nice. So how do you find this thing here? This dude right here is provided by this formula, f at t naught, y naught. That's the derivative, the true value of the derivative. And then we'll have it times h. And then this is actually just y naught, the given initial condition. So let me stop a second. I promise you, but it's like, in Disney's, it's just like the next stop. It's just like a red lobster blocking your view or something. Oh God, okay, so this is equal to y naught plus f at t naught, y naught, h, plus this stuff right here, and that stuff is an order h squared expression. Take that order h cubed stuff, but then we tacked on this order h squared stuff. So check this out, that the true y1 is this. So let me stop for a second. Look at that. Think about what is Euler's method. What do you see in here that resembles Euler's method? This. That is our approximate y1 right there. So Euler's method is really just about a Taylor series that's truncated, and we're grabbing the constant and linear terms of it. So just see right over there, just that y1. So this is approximate y1 right there. So now we see that the true y1 equals the approximate y1 plus some order h squared stuff, and we can generalize this, or not generalize this, just make this look a little bit more error-like, that the error on the first step is an order h squared error. Yeah, that sucks. I'm sorry. It's too late in the semester for me to be playing with that anymore. We need some bar stools in the back.
Oh.
Yeah. What is it? You okay?
Look,
Did you find something cool?
I found that paperclip stuck to my iPad for something.
Oh, geez.
I stole the lens.
So each single step of Euler's method has order h squared error. What does that mean? That means that if h is 0.1, I can assume that my approximation is within 1/100th of the truth. If h is 0.01, that first step is going to give me a 1/10,000th of the truth. That's actually pretty good. Does that make sense what I'm saying about the error? Like how that works and what that h squared stuff means? You take your step size, you square it, that's within a constant of that, you'll be near the truth. Okay, so we do this for each step, but we do it a bunch of times, and so error tends to propagate. You make this first step from t naught, y naught, you make your first step there, and here's your y1, but here's the truth. And so immediately you've got error in that. So let's see if this is t naught plus h. This is order h squared difference right there. And then I do it again. So I'm moving from here, and I started off on the wrong foot, and that wrong foot is going to become many wrong feet stacked together. So the error propagates over the b minus a over h, and we would probably round that up. That is the ceiling function. It means round up to the next full number. Steps. And what I'm assuming here is if our solution is on some interval a to b. So take the length of the interval, divide it by h, the step size, and that should give you how many steps it takes to get across. But it probably won't be a whole number, so round up to make sure you get all the way across. So after that, the error propagates, and one can show, we're not going to show, the book doesn't even show. The book is like, this is a lot of hocus pocus, but one can show. So one can, we don't know, we'll have to find that one, pay them well. One can show that after b minus a over h steps, the global error, so after the process is done, is actually you lose some precision, is an order h. So what does that mean? That means that if my step size was this, that at the end, that final estimate at the end has that as the error. Each step had this is the error, but then the propagation like just pulls you back down. So it is an order H technique, and God, I've got a formula here for it. Let's not. Any questions on this? Because I kind of want to move on to how to make this better. Yeah? Okay, cool. So improving on Euler's method is very cool. And once you see how it works, you'll understand all Runge-Kutta methods forevermore. So improving Euler's method. So what we get is a family of methods. Each improves the global error. And these methods are called Runge-Kutta methods. Runge with an E, Kutta methods. Euler's is Runge-Kutta 1. And I guess there's no 1 there. And the number is the order of the error, the global error. So this 1 represents the global error order. So h to the 1, we just talked about. So let's talk about RK2. How do we actually get the h squared error on the global process? After I've done n steps, how can I be assured that, yeah, we've done better than Euler's going to do for us? And it's a pretty cool idea. So let me show you what the idea is. Idea. Step 1 is start off a lot like you would with Euler's. So again, the problem we're solving is y prime is f of ty, y of t naught is y naught. So we've got this initial point. And we want a solution, on some closed interval a, b. And a is your t naught here. A is the left end of your interval. So what we're going to do, first off, has anybody in here used Runge-Kutta? Like somebody told you to use it? And yeah, Josephine, you have?
Yeah.
Cool. Do you have a sense about how it works? And I'm not going to make you come up and lecture.
Mostly, like 2 years, 2.5.
It was a while
since I did
ago.
it.
Cool. This will bring back good memories.
Yeah.
Nice. Anybody else use this? Are you work with Dr. Gray?
No, it was for my NASA project and I had to teach myself over YouTube videos.
Oh my goodness. Amazing. That's awesome. That's so awesome. But suffice to say, these Runge-Kutta methods are really used. This stuff is all over the place. Now, this RK2, this is like the learner's permit version. RK4 is where most work gets done. So it's an order h to the 4th method. And we'll get there in just a second. But if you understand this, you've got that. So how does this work? Well, so start off 1, get S1, which is your initial slope estimate. So this is a lot like, and this S stands for slope. So this is just like Euler's, initial slope. S1 equals initial slope. And then what we're going to do is not move in that direction yet, but we're going to sample in that direction. We're going to reach out into the future, see what's going on out there, and then come back to the present and incorporate that future information into our present estimate. So we get S1, and so we have step size h. H equals step size, as always. And let's say this is t naught plus h right here. So what I'll do is I will find the slope right here, and let's say that that's that slope. So that has slope S1. I'm going to head out either the whole distance or a fraction of that distance and grab the slope at that point. So step 2 is reach our sample forward to get the slope at f of t naught plus alpha h. So this alpha is going to be a number between 0 and 1. It's the percent of how, wow, it's the percent of how far I want to reach forward. Alpha equals a fraction of the whole step we sample at. So you literally can. You could, alpha, so put equals to 1 there. Alpha could go all the way to that right end, and we could grab where the next step would fall if we kept following that arrow. Sorry. So reach forward to get that, and so that's going to be t there, and then we're going to have y naught, our initial condition, plus alpha h f of t naught y naught. So check this out. This is a little complicated looking because we've got these nested functions, but this just says this is the slope, current slope, and I move forward a fraction of h upward as well as the fraction of h over. So what I'm going to do is move this way, and this S1 is equal to f at t naught y naught. I'm going to move over, let's say that's my t naught plus alpha h right there. So I'm going to make, the arrow's going to have that horizontal component, and then the vertical component is just a scaling of how far I normally would have gone up. So this distance right here is alpha h f at t naught y naught. That is a sub-zero there. Now, let me stop because there's a lot of, the first time you see this it looks super complicated, but the idea really is reach into the future, grab that information, come back with it. So this is S2. This is our estimated, or this is our just future slope. If we had gone on the Euler's journey, if we had taken Euler's method a fraction forward, a fraction alpha forward. So grab S1. Then we're pretty much about done. What we're going to do is take a weighted average of the current slope with the future slope and use that as the direction we head. So what I mean in particular is, let's see, so 1, 2, 3, use a, I'll just write out what I said, a weighted average of S1, remember that is current slope, and S2, this is future slope. Again, not necessarily the true future slope, but the one Euler's would give us if we had kept on Eulering our way through this. So find a weighted average of these, and the way it basically works is we take 1 minus alpha times the current slope. So we're weighting this current slope, well, I'll just put it, I guess it depends on what alpha is, S2. So this is a weighted average. And this is going to be the slope we use. So head out using this slope. And so that means our y1, our update, is going to be our current y plus this. So this is the slope. Now I have to grab, yeah, hold on, let me just double check my notes here. Yep, okay, yay, I'm not insane, at least here, doing this. We're gonna head out and have that times h. And then we'll take the full step, but using this new composite slope. repeat. Now this all just repeats. So step 4 is let T naught, T1 equals T naught plus H. So you update your T, Y1 equals this, and repeat. Plot that point, do it again. Plot that point, do it again. So RK2 is, the 2 is the number of times, the number of pieces of data we're using to estimate our slope, but it's also the order of error. This is an order H squared method. That's kind of neat. It's not all that much. This is really easy to code. I mean, the code is almost right here. You'll see the code, it's super simple. So how do we make this better? Well, there's an RK3. We'll reach forward 3 times, nobody uses that. Why would you be like, I'm up for 3 times, but I just can't stomach 4 times forward. Like, why would you not do that? So RK4, let's talk about how this kind of works. I got to grab my notes on this because the things get, oh, actually, let's talk here really quick just about the alphas. So if alpha equals a half, what that means is that you're reaching, if this is the H step here, you're reaching halfway across. So your samples are here. And this is H over 2 forward. That's called the midpoint method, not shockingly in any way, shape, or form. Let's see, I'll write this up here. Oh wow, that is pretty much the end of my notes. I made notes in the code. Oh, here we go, look at me, what a fine young man I am. If alpha equals 1, that means I literally go the full step. So if this is H right here, this is my current point, I follow that Euler's method all the way to the end and I grab it. Any ideas on maybe what method this is called? You've seen the word before.
Trapezoid.
There you go. Yeah, exactly. There's a trapezoid right there. This is called the trapezoid method. And then lastly, if, what was the Hans method? Alpha equals 2/3. Oh no. If alpha equals 2/3, this is called the Ralston method. Ralston's method. And it turns out that this is the most efficient alpha you can use. This one gives you the best accuracy, best bang for your buck. And that's a 2/3, 2/3 step. So you're here, you move over here, you just move 2/3 of H over, grab that, and grab that average, saying that's the full H right there. Probably the most common. I think this method here, midpoint, but I actually think this might also be called Hans method. One of these two is Hans. I'm a little fuzzy on which one. All right, let's RK4 it. Get some code running. Call it a break. That being said, I gotta talk to myself. You will, buddy. You're not gonna watch this. You're talking to me. I will create a video that I would like you to watch over the break. Now, I'm not ending class, so don't get excited. No need to get, this isn't ending. We have time left. I'm gonna create a video over the break that honestly is absolutely essential for you to watch over the break because it's the hardest part of what this unit is about. And even you DiffEQ savvy folks, this is going to be new. This is going to be challenging. So, and I'll actually work some problems with you in it and give you some time. So please watch, work along. That'll be your homework. There's no more homework except the final exam that I will give you after we return. We'll take some time in class to work on it. It'll be due the end of finals week on Friday. And I'll have office hours, all sorts of stuff. So nothing to stress about. Hopefully you've kind of like learned to maybe, I don't know, maybe your experience of this class is way different than I think it is. But I don't think it's been super brutal, right? And don't say easy, because then that'll hurt. And I'll have to become mean. And people will blame you. You don't want that. So let's talk about RK4. Runge-Kutta, fourth order method, 4 samples. We're gonna grab 4 samples. So what's the plan here? T-naught. Why not? Definitely gonna use our current location. That would be madness. To not look at what's under your feet. What else are we gonna do? So we're gonna say that S1 equals, actually here, let's make this a little more general. That's T sub n, that's Y sub n. We're at the nth step of this process, because really it's just the same thing over and over again. We're gonna update our T, so Tn plus 1 is the current T plus H. Update. Move over, we'll grab that in the future after we do all these slopes. So S1 is your current slope. Current slope. S2. With S2, we're going to take our current slope, and if this is Tn plus 1 over here and this whole thing is H, we're going to follow that current slope halfway across. So we're going to move over half the distance, grab the slope here. That means we go up half the predicted increase, half the increase I would have if I went all the way over here. And I'm going to grab that estimate right there. So S2 is F of T of n. We got to move the T over, so we move it over T, H plus 2 units. And then the Y sub n, the Y sub n I'm sampling from is half the step size times the current slope. If these were the only things I was using, it's the midpoint rule. So if I just took an average of these things, half of this and half of this, I would be using the midpoint rule. But I'm not. I'm just grabbing that right there. And then S3, let's write it out and then talk about what it says. And maybe you can think about it for a second. S3 is F of T sub n plus H over 2, Y sub n plus H over 2, S2. They sure look the same. Come up in your head with a sentence of what's different. What did we do? So like, just take a minute, don't say it out loud. In your head, how would you explain to someone S3? You're such a kind person, Trey. No one has scooted more for me than you, ever. Anyone care to regale us with tales of S3? Okay, you said it's your first hand up. Okay, timid hand, but go for it.
Is it like, instead of moving at the slope of like your current point, like that estimate, it's like if you went at the slope of your midpoint at your current point.
Yeah, exactly. That's 100% it. So let's say that, you know, the slope here was like that, but the slope out here was like that. So what I'm doing is I'm coming out here, halfway across, moving up, whatever this, so shit. Okay, so hold on. I'm moving at this slope, and this slope wasn't my current slope. This slope was the slope halfway across. So I look at this slope here, grab this, that is S2 right there. So S2 is this slope. And what I'm going to do is move over again, that same halfway point, but I'm going to move up half of that slope. So notice that if I did that, and let me make this a little bit more movie, so it's like that. So I'll put that here. So I come back to here, and now I move at that slope over. And I'm going to grab the slope there. Grab them, and then I've got my original. Clearly I'm amusing myself. S4 is going to use S3. So now we've got this weird, now we're grabbing the slope here. Now we're grabbing the slope there. And what we're going to do is compute what our slope would be using that slope. So what is that slope right there that came from here? So that is f at Tn. Oh no, we actually we don't do halfway. We actually grab that slope there, but then head all the way across and grab that. That's it. So check this out. First slope, local. Middle two, grabbed. Grab this one recursively. Use that slope to get this one. Use that one to now move all the way across the full step size and grab that slope over there. So what does that look like? That is Yn plus HS3. So now we've gone a full step size. So we're really grabbing a lot of information. 2 in the middle, 2 on the ends. And the ones past the beginning all feed off of each other. We're using them to predict the next one. So we're going to grab this slope, this slope, this slope, and then this slope, whatever that is. So we're like fanning out, taking a bunch of things that could be our future and grabbing those, and we're going to create a weighted average of them. And the weighted average is interesting. There. Weighted average looks like this. So Yn plus, well, this is now our update. So we're gonna, our new Y value is our old Y value plus our step size times S1 plus 2S2 plus 2S3 plus S4 over 6. So notice the weights are 1, 2, 2, 1. The weights add up to 6. And then we divide by 6. Notice we are weighting the halfway steps twice as much as the start and the end, which makes sense, right? Because we moved out here, but we're less certain about that information than anything. And this information we're just going to count. We're going to make this a little heavier and value it a little bit more. But that's it. Repeat. So crazy. Cool scheme. These weights, RK4, I've never seen different weights. So unlike the RK2 where we have variable weighting, these are the weights. That's it. So let's look at code. And then in this code, I've got got a damn good question for you. You can help me understand why something looks so insane. So the code should be, there's a new content folder, Runge-Kutta something. This computer looks on. Okay. No signal. Of course there's no signal. Even though the computer is on. Well, you can. You're going to want to cut and paste that code into a Jupyter notebook and run it. And I just want to look at it with you so bad.
I don't see the folder.
What? Oh, fuck. Okay, hold on.
Not to make
No,
it
no,
worse.
it's. I might have set the unlock date. I'm just so I've just been trained by over-eager students to like lock things up, lock the liquor cabinet until I come home. I don't want people getting in there and learning prematurely. Mostly because I just want to have all this. I want to have fun together. What is that? This sound bar? Okay. So let's see. We've got two things of those that work. This needs to break. Just run the code. I'll probably just have to come around. Oh, this is good. The keyboard lit up. Yes. Fantastic. Let me see what you're seeing. Oh, you can't. You can't see anything because the fucking stuff is. I was trying.
My laptop died and I'm not doing the work, but I.
No, it's okay. It's okay. I was like, I did post a lot of jewelry. So if you want to buy anything, let me know. Yeah, you can't do anything. You found it?
No.
Oh, okay.
It's like, yeah, there's nothing.
Okay, well,
Sorry.
it's okay. Oh, this looks... I'm seeing a BIOS window. Invalid setup. Configuration. Invalid configuration. Hold on. Oh boy, I really locked the liquor cabinet. I lost the key. We desperately need a drink. Smash it. I have to make toilet hooch. I learned that. I learned from some of the folks I worked with in Inside Out how to do that. You ever seen that? Anybody ever seen that? Yeah, Cormac has. Cormac and I spent some time together in a institution
On the inside.
years back. We were cellmates. Every Friday we'd brew up a batch, sell it, so we could buy smokes.
It was a simpler time.
It was a simpler time in ways I long. Yeah, same. It's also a terrifying time. Well, I can just really spew the bullshit out when I'm in the mood. It's not quality bullshit, but. Alright, let me get there. I'm finally up. Oh my god, I didn't have to do all the verification stuff. Imagine. Now I'm getting a little scared. Because it's almost like I didn't save it.
Oh, that's fun.
Oh, damn it! Oh, man. Well, shit. Well, I don't have it. And and quite frankly, it was way too much work to reproduce on the spot. So it will be how I start my extra lecture. How's that sound? We get out a little early today. No one's going to be too upset. Thanks. Keep an eye out. Keep an eye out. I'm definitely going to put an Easter egg that you need to find in that lecture.
I was already waiting for it.
I don't know. It's cool. It's cool. It's coming. Don't worry. I know. I'm sorry. I was thinking about you most of all. I knew you'd be really constantly refreshing.
Oh no, I just skipped through the video so I could just find it and then watch the video later.
Oh, okay. So I have to somehow try to figure out how to work around that. Have a good day.
It's so funny.
Exactly.
Bye.
It's like a club.
It does suck.